the harmonic series again. We've already seen that the harmonic series diverges. So we've shown that the harmonic series diverges by grouping together the terms and then showing that each of the groups is bigger than 1/2. So summing the harmonic series is even worse than summing 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 and so on. We can also check this with the integral test. So let's set a sub n equal 1 over n. And I'm trying to analyze the convergence of the series. N goes from 1 to infinity of a sub n. That's just the harmonic series. And to help me, I'll look at the function f of x, which is 1 over x. And note that a sub n is f of n. I want to make sure that f is positive and decreasing. Right, so I need the function f to be positive and decreasing on the interval that I care about, which is the interval from 1 to infinity. Well, I know that f is positive because if x is at least 1, even if x is at least 0, right, f of x, which is 1 over x, is positive. I mean, the reciprocal of a positive number is positive. Now I need to check that f is decreasing. And what that means is that if a is bigger than b, then I need that f of a is less than f of b on the interval that I'm thinking about here. Well, that's true, because if I've got a and b, say they're both positive numbers even, then how does 1 over a compare to 1 over b if a is bigger than b? Well, if I've got a larger positive number, but I take its reciprocal, now it's smaller. So this is telling me that f is a decreasing function. Now I'll check that the integral diverges. Well, let's compute the integral from 1 to infinity of f of x dx. Now, by definition, this integral is the limit as big N approaches infinity of the integral from 1 to big N of f of x dx. Now in this case, f is just the 1 over function, right? It's the function that sends x to 1 over x. So this is the limit as big N approaches infinity of the integral from 1 to big N, just 1 over x dx. Now to compute this definite integral, I'm going to use the fundamental theorem of calculus and recall that an antiderivative for the 1 over x function is the natural logarithm. So by the fundamental theorem of calculus, this is the limit as n approaches infinity of an antiderivative, which is the natural log, at the one endpoint minus the antiderivative, natural log, at the other endpoint. But now log of 1 is 0, so this is just asking what's the limit as n approaches infinity of the natural log of n, right? What happens when you take the natural log of an enormous number? Well, admittedly, it's less enormous, but it's still as large as you'd like, right? By choosing big N big enough, I can make log n as large as you'd like, which is just to say that the limit of log n as n approaches infinity is infinity. So this integral diverges. So the same is true of the series. Right, so by the integral test, the sum, n goes from 1 to infinity of 1 over n, the harmonic series diverges as well. So now we've got two proofs that the harmonic series diverges. Anytime in mathematics that you've got two different proofs of the same theorem, it's worth thinking about how those proofs relate. In this case, which proof do you think is easier? I mean, in a certain sense, the integral test is easier. It requires less creativity to just integrate 1 over x than to do that complicated grouping. And yet the grouping argument predates integration, right? The grouping argument is from the 1300s, and integration, right, wasn't really around until Newton, say. So yes, although the integral test seems like the easier way to show that the harmonic series diverges, the integral test is depending on the huge edifice of calculus. It's requiring more technology. And the grouping argument, while somehow requiring more creativity, doesn't require so much theory to be built up.